Hello viewers, today in this program I am going to deliver a lecture on application of integral calculus. Integral calculus have various application in mathematical sciences and in engineering. Actually, integral calculus has numerous application. It is used to computing the area of the curve, the arc length of the curve, surface area, volume of the solid, and for finding center of mass, moment of inertia, etc. Here I will explain you some of them. First one is arc length. Let AB be an arc of the curve as shown in the figure. Consider n plus 1 points A0, A1, A2 dash 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 An on the arc such that as shown in the figure. Length of the arc AB is defined to be the limit of sum of the line segments A0, A1, A2 dash 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 An and An minus 1 An as n tends to infinity. In the Cartesian form, let the equation of the curve in Cartesian form be y is equal to fx. Let a x naught y naught be a fixed point on the curve from which arc length is to be measured. Let p x y be any point on the curve and s be the length of the arc AP. Let q x plus delta x, y plus delta y be a neighboring point of P and the length of the arc PQ be s plus delta s as shown in the figure. See, from this figure we have PQ square is equal to del x square plus del y square. Dividing both sides by del x square and rewriting, we have PQ upon del x whole square is equal to 1 plus del y over del x whole square, or PQ over del s whole square into del s upon del x whole square is equal to 1 plus del y upon del x whole square, making limit q tend to p so that delta x tend to 0. We have PQ tend to 0 and the limit becomes limit del x tend to 0, del s upon PQ is equal to 1. Thus, taking limit as del x tend to 0, we have limit del x tend to 0 PQ upon del s whole square multiplied by limit del x tend to 0 del s upon del x whole square is equal to 1 plus limit del x tend to 0 del y over del x whole square. It becomes ds over dx whole square is equal to 1 plus dy upon dx whole square. Assuming that arc length s increases as x increases so that ds upon dx is positive, we can write ds upon dx is equal to root 1 plus dy by dx whole square. Equation 1 gives the rate of change of arc length with respect to x. The differential of arc length is given by ds upon dx is equal to root 1 plus dy by dx whole square. Therefore, ds is equal to under root dx whole square plus dy whole square. Thus, between any 2 point x1 y1 and x2 y2 on the curve, the length of arc between the point is given by s is equal to integration of the integrand 1 plus dy by dx whole square with respect to x from the limit x1 x2. If any equation of the curve in Cartesian form is x is equal to fx, the rate of change of arc length with respect to y is given by ds upon dx is equal to under root 1 plus dy by dx whole square. For example, find the arc length of the asteroid. You all know about the asteroid. it is given by x to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3. Differentiating both sides, we find 2 by 3 x to the power 1 by 3 plus 2 by 3 y to the power 1 by 3 dy by dx is equal to 0. Therefore, dy by dx is equal to minus y over x to the power 1 upon 3. The asteroid shown in the figure, it is symmetrical about x axis as well as y axis. Therefore, we find the arc length in one quadrant and multiply by 4 to find whole length. Hence, the arc length s of the asteroid is given by 4 times integral from 0 to a, integrand here is under root 1 plus dy by dx whole square with respect to x. It is equal to 4 times integral from 0 to a under root 1 plus y to the power 2 by 3 divided by x to the power 2 by 3 integrate with respect to dx. It becomes on simplification equal to 6x. Hence, the arc length s of the whole asteroid is 6 times a. Now, I will explain you parametric form of the curve to find the arc length. Let the curve be described by the parametric equation. X is a function of t and y is another function of t, where t is some parameter which varies from t1 to t2. Differentiating x and y with respect to t respectively, we find dx upon dt is equal to x dot and dy by dt is equal to y dot. Then the arc length s is given by integration from t1 to t2 under root x dot square plus y dot square with respect to t. For example, find the arc length of the curve x is equal to e to the power t cos t, y is equal to e to the power t sin t. Between the points corresponding to t is equal to 0 to t is equal to pi by 2. We have x is equal to e to the power t cos t and y is equal to e to the power t sin t. Differentiating x and y with respect to t, we have x dot is equal to e to the power t bracket cos t minus sin t and y dot is equal to e to the power t cos t plus sin t. We put these values in the formula and we have x dot square plus y dot square is equal to, on simplification, root 2 e to the power t. So, we integrate root 2 e to the power t from 0 to pi by 2 and find root 2 bracket e to the power pi by 2 minus 1 as the result of arc length of this curve in parametric form. Similarly, I will explain now polar form of the curve and how to find the arc length of the polar curve. Here s is equal to integral theta 1 to theta 2 under root r square plus dr upon d theta whole square d theta. For example, consider the curve r is equal to a 1 minus cos theta in polar form. This is the equation of cardioid in general form. Differentiating this, r is equal to a 1 minus cos theta with respect to theta, we find dr upon d theta is equal to a sin theta and hence ds is equal to under root r square plus dr upon d theta whole square d theta becomes under root a square minus 2a square cos theta plus a square cos square theta plus a square sin square theta d theta. On simplification, it becomes 2a sin theta by 2 d theta. The curve for r is equal to a 1 minus cos theta is as shown in the figure. So, it is symmetrical with respect to initial line Hence, we double our arc length using the formula S is equal to 2 integral 0 to pi ds, that is equal to 4a integral 0 to pi sin theta by 2 ds, that is on simplification gives us 8a. So, the total arc length of the cardioid is 8a. Now, I will explain you the area as double integral. Area as limit x tend to 0, y tend to 0, sigma del x del y, that is equal to double integral over the r dx dy. Example to explain the procedure of area bounded by double integration is as follows. Suppose it is required to find area of the ellipse x square upon a square plus y square upon b square is equal to 1 in the first quadrant of xy plane. The portion of ellipse in the first quadrant of the xy plane may be described by the equations x from 0 to a. So, 0 less than equal to x less than equal to a, and similarly y is from 0 to b by a root a square minus x square. Thus, the required area is integral 0 to a second integral 0 to b by a root a square minus x square dx dy, which is the double integral. The area is given by, on simplification this, after putting x is equal to a sin theta and performing integration, we find the area of the ellipse, 1/4 part of the ellipse is pi by 4 ab. As you all know, whole area of the ellipse is pi ab. Second example here is find the area common to the circle r is equal to a and r is equal to root 2 cos theta. As shown in the figure, there are two circles and we want to find common area of the two circles. The two circles r is equal to a and r is equal to root 2 cos theta intersect when root 2 cos theta is equal to a. Therefore, theta is equal to pi by 4 in the positive quadrant and in the negative quadrant. So, the limit here is theta is equal to minus pi by 4 to plus pi by 4 as shown in the figure. Thus, the area of the curve is given by integral from theta is equal to minus pi by 4 to theta is equal to pi by 4 and r is equal to 0 to a r dr d theta, that is equal to integral minus pi by 4 to pi by 4. Integral here is r square by 2 from the limit 0 to a d theta, that is equal to integral minus pi by 4 to pi by 4 a square by 2 d theta, that is equal to a square by 2 theta from the limit minus pi by 4 to pi by 4. On simplification, it becomes a square by 4 pi, that is the total area of the curve bounded by the two circle. Now, I will explain you an important application of integral calculus, that is to find volume of solid generated by revolution of a curve about some axis. Let us suppose a curve revolve about x axis, then it generate a solid. We will find the volume of the solid thus generated using the integral calculus as follows. The revolution about x axis, let us suppose AB is the arc of the curve y is equal to fx lying between the ordinates x is equal to a and x is equal to b. We assume that f is continuous in AB and that it does not meet the x axis anywhere. Let p x y and q x plus delta x y plus delta y be two neighboring points on the curve y is equal to fx. Draw Pm perpendicular to Ox and Qn perpendicular to Oy. Draw PR perpendicular to Qn and SQ perpendicular to Pm as shown in the figure. Let V be the volume of the solid generated by the revolution about the x-axis of the area ACMP. As x increases, MP moves towards the right and the volume increases. Let the volume of the revolution obtained by revolving the area ACNQ about x-axis be V plus delta V, so that the volume of the solid generated by the revolution of the strip PMNQ about x-axis is delta V. We now have Pm is equal to y and Qn is equal to y plus delta q. Therefore, Mn is equal to x plus delta x minus x, that is equal to delta x. Then the volume of the solid generated by revolving the area PMNQ is x multiplied by y plus delta y whole square delta x. We further observe that the volume of the solid generated by the revolution of the area PMNQ lies between the volumes of the right circular cylinder generated by the revolution of the area PMNR and PMNQ. Thus, delta V lies between pi y square dx and pi y plus delta y whole square dx. Therefore, delta V over delta x lies between pi y square and pi y plus delta y whole square, and so pi y square is less than delta V over delta x less than pi y plus delta y whole square. In the limiting case, as q approaches p, delta x tend to 0 and delta y tend to 0. Therefore, delta V over delta x becomes pi y square, or dV becomes pi y square dx. Therefore, the integral from a to b pi y square dx represents the volume integral a to b dV, that is equal to Vb minus Va, that is the volume generated by the area formed by the revolution of the curve. Now, I will explain the example for the same. Find the volume of solid generated by revolving ellipse x square upon a square plus y square upon b square is equal to 1 about its major axis, that is x axis. Solution of the problem is as follows. The ellipse x square upon a square plus y square upon b square is equal to 1 is symmetrical about y axis. Therefore, the volume generated by the ellipse by the revolution about x axis is twice the volume generated by the area in the first quadrant about the x axis. Therefore, required volume is equal to twice the volume from 0 to a pi y square dx, that is equal to twice integral from 0 to a pi y square here is b square upon a square bracket a square minus x square. So, we integrate this integrand over dx is equal to twice of pi b square upon a square integral from 0 to a square minus x square dx, that is equal to 4 upon 3 pi a b square. Now, I will explain you the volume of solid of revolution in parametric form. It is given by pi integral a to b phi t whole square psi dash t dt, where phi t is the function representing x and psi t is the function representing y. Similarly, the volume of solid of revolution in polar curve is given by integral from alpha to beta 2 by 3 pi r cube cos theta d theta, where x is r cos theta, y is r sin theta. Now, I will explain the surface of solid of revolution. If a curve revolve about x axis, it generate a solid. We find the surface area of the solid thus generated using the following method. For the Cartesian curve, let AB be the arc of the function y is equal to f x included between the ordinates x is equal to a and x is equal to b. Assume that the curve does not cut x axis. Let p x y and q x plus delta x, y plus delta y be any two neighboring points on the curve. Let length of the curve AP be s and that of the arc AQ be s plus delta s, so that the arc PQ is of length delta s. Draw the ordinate PM and QN. Let S denote the curved surface of the solid generated by the revolution of the area CMPA about x axis. The curved surface of the solid generated by the revolution of the area MNQP is delta S without any loss of generated by the revolution of the area MNPQ about x axis lies between the curved surface of the right circular cylinder whose radii are PM and QN and which are of the same thickness delta S. Therefore, delta S lies between 2 pi y ds and 2 pi y plus delta y ds, that is 2 pi y ds is less than delta S less than 2 pi y plus delta y ds. Therefore, 2 pi y is less than delta S upon delta small s less than 2 pi y plus delta y. As shown in the figure, Q tend to P, that is, as delta S tend to 0, delta y will tend to 0. Therefore, the surface integral is given by integral from a to b 2 pi y ds, that is equal to a to b ds s from a to b. Hence, the required curved surface is given by integral x is equal to a to b 2 pi y ds, where ds is given by under root 1 plus dy by dx whole square dx. Here ds is the arc length of the curve from a to b. Now, I will explain the surface of solid of revolution in another type of equation. Let us suppose the equation of the curve is given in parametric form, then the surface area is given by integral a to b 2 pi y ds upon dt dt, where ds upon dt is given by root dx upon dt whole square plus dy upon dt whole square, where the t is the parameter, x is the function of t and y is some another function of t. Similarly, the surface of solid of revolution in polar curve is given by s is equal to integral from alpha to beta 2 pi y ds upon d theta, where ds upon d theta is equal to root r square plus dr upon d theta whole square, and y is equal to r sin theta here in the polar form. Hello viewers, in this program I have explained you the application of integral calculus in various fields. I have explained first of all the line integral, the arc length of the curve between A and B we can find using the integral calculus. Then I have explained the area bounded by the curve. We can find area bounded by the curve using the integral calculus, and then I have explained with example the surface and volume of solid of revolution, which can be obtained by using the integral pi y square dx, that is the volume of solid of revolution, and 2 pi y ds, integration of 2 pi y dx, that is the surface area generated by revolution of the curve about x axis. Hope you have enjoyed the lecture. Thank you.